Let's take a look at section 2.6, special functions. When we're looking at special functions, in order to do well with this, you really want to have a strong understanding of our transformations of graphs, which we did last section. It'll really help you graph these a lot quicker and more efficiently. So let's just review what we've learned so far. The functions we've discussed are constant functions, which are a horizontal line. Linear functions that are y equals mx plus b. The parent is y equals x. Quadratic functions, which is our parabola. Our parent function is y equals x squared. And our absolute value functions, which are v's, and our parent function is y equals the absolute value of x. So let's just review a practice of our transformations. We'll do number 1 together. If we remember, the parent function of this is just y equals x squared. It's going to be a parabola, but let's talk about what the transformations are. We have a 2 out front, so we have a stretch. We're subtracting 5 on the inside, so we're going to go to the right 5. And we're adding 1 on the outside, which means we're going to go up 1. So remember when we were graphing these, okay, I would go to where my parent function usually is, which is at the origin, but I'm going to use those transformations. So instead of the vertex being at the origin, I'm going to go to the right 5 and up 1. Here's my new vertex. Now, normally from there, we would go up 1 over 1, and then up 4 and over 2. Remember, those are the key points you want to have memorized from a parabola. But this time, we have a stretch of 2. So instead of just going up 1 over 1, I'm going to go up 2 over 1 and up 2 over 1. Then back to my vertex, instead of going up 4 over 2, I'm going to go up 8 units and over 2. Notice the amount I'm going over horizontally isn't changing. The amount I'm going up and down vertically changes because it's a vertical stretch. And so now I can connect those dots and have my curve. Now that we have our graph, we can state our vertex and identify the domain and range. So my vertex for this problem, like we said, originally parent graph's at 0, 0, but we moved to the right 5 and up 1, so the vertex is 5, 1. My domain for a parabola, if we look to the left, we look to the right, we technically go up and to the left forever and up and to the right forever. So my domain is going to be all real numbers. My range is looking up and down. So do I go down forever on this parabola? Well, the lowest this parabola is going is at 1. Do I go up forever? And yes, I do. The arrows indicate to go up. So with interval notation, I include 1, it's included, and it goes to infinity. Okay, you try 2. Remember, the parent function of that one is an absolute value. Now that we have reviewed those, let's take a look at some more special functions. So the first one we're going to discuss is a piecewise function. A piecewise function contains exactly what it says, pieces. So we're going to have 2 or more parts to our graph. And what that usually means is that it'll be a little bit more choppy than normal. So if we look at our first example, we have 2 equations as part of this. X minus 1 all squared and x plus 3. What that's saying is I'm going to have part of a parabola being graphed and part of a line being graphed. And it's just going to be part of them because I'm only going to plot this first graph for when all x values are greater than or equal to 1. So here's my x values of 1. I'm only going to have a parabola on this end of my graph. Then I have a linear equation for all values less than 1. So over here towards the second and third quadrant will be the linear. So how do I go about doing this? We have 2 options. I'm going to use blue to represent this first graph. And I'm just going to graph this as normal. If I was to graph x minus 1 all squared, what that is normally at our vertex, but it's moving to the right one. So I'm going to now move that vertex to the right one. Then a parabola, there's no other transformation, so then a parabola usually goes up 1 over 1, on both ends, and up 4 over 2. However, we do not want to actually connect all the dots here. This would be the graph for all real numbers. We only want to graph this parabola for x values greater than or equal to 1. So what that means is I need to erase everything below x values of 1. So notice here, here's my x value of 1, x value of 2, 3, 4. Those are all greater than. So I'm just going to have, and now I'll connect it solid, I'm just going to have this as my piece of the parabola. Nothing where x values are less than 1. Now I'm going to graph the second part. The second part is a linear equation. I'll do that in red. How do I graph a linear equation? I plot the y-intercept, and then the slope says to go up 1 over 1 or down 1 over 1. And I would go about connecting those points. However, we only want to graph for values that are less than 1. So if I go to 1, what I need to do is I need to alter this. I need to make at 1 an actual open circle because I'm not including it, but we need to make sure we account for 0.999 and so forth. And then I want my line only plotted for values less than 1. So x values less than 1 are the ones to the left here. So I can connect down 1 over 1. Oops, sorry, it's not exactly straight. I can connect the line there, and I'm going to erase the dotted part. And I certainly need to erase for all values that are greater than 1. So here is my piecewise function. I have two pieces because there were two equations. I have part of a parabola for x values greater than 1, and I have part of a line for all x values less than 1. Now what we're going to do is we're going to evaluate the function for f of 3. So when I say f of 3, usually that means we plug 3 in. However, we have two pieces, so where do I plug it in? For this one, our x value of 3 is greater than 1. Therefore, we're going to plug it in to that top equation because that's saying use this equation for all x values that are greater than 1. So when we do that, we're going to have 3 minus 1 all squared, and that gives me 2 squared, which is 4. So f of 3 equals 4. And we can even look at that on our chart. Here's the x value of 3. Let's go up. Bingo. It hits at 4. Okay, so with our piecewise functions, you can think about graphing each individual equation, but then make sure to erase the parts depending upon what our domain needs to be. Now let's look at a step function. A step function is a type of a piecewise function, but it just contains a bunch of horizontal line segments, aka creating steps. So this is pretty straightforward. What it's saying here is that my graph needs to equal -4, so f of x, aka the y value. So if I go down to my y value of -4, my graph is going to be at -4 for x values that are between -5 and -3. So here's -5, and I want to equal -4. And I'm going to have a closed circle there because it's included. Now we're staying equal to -4 until my x value is -3. Here's the x value of -3. And so there I put an open circle. So I just graphed that first piece. Now let's graph the second piece. It's saying, okay, now jump to the y value of -1. And I'm going to be -1 from -3, and it's included. Oops. Just plotted down at -2. And it's included until -1, open circle. Now let's graph the third piece. The third piece says make my y value 2 from -1, so my x value is -1, it's included, until my x value is +1 and it's not included. So now we have this sort of step function where I'm jumping from one horizontal to the next to the next. Okay, so a step function is a type of a piecewise function. Notice 3 pieces in this one, but they'll always be horizontal line segments. Okay, now we have our greatest integer function, which is our last type of special function we're going to discuss. A greatest integer function is also a step function, but we need to learn a little bit more about it. So this is a new symbol, brackets. When you see something with brackets, it's indicating greatest integer function. And what a greatest integer function is to round down. So normally our rounding rules are at, once we hit 0.5, we round up. These will always be to round down. So for example, if I say in this case, f of negative 0.5, what that is saying the greatest integer of negative 0.5, and so it's saying round down. So when I round negative 0.5 down, that gives me -1. Let's do a couple more. If I said f of 0.5 or 0.25, that would be saying what's the greatest integer of 0.25? And that is 0, rounding down. Same thing, f of 0.9. That's saying round down to the closest integer, which would also be 0. So notice 2 values here, and they both have the same answer. That's what's going to create a horizontal interval there and a step, because we're saying we have multiple x values that give us the same y value. We'll do one more. How about f of 1.8? F of 1.8 is saying the greatest integer of 1.8, which rounding down gives me 1. So what you want to have memorized is what the parent function looks like. And here is the parent function. We start at our origin. Each step is going to be 1 unit long and an open circle on the right of each step. We jump up 1. Now we're at 1, 1, closed circle, horizontal of 1 unit, and an open circle. We continue with that pattern. So for my parent function, every step is 1 unit wide, and we jump up 1 unit. The opens are on the right-hand side, and the closed circles are on the left-hand side. And we could go on and on forever, but 5 steps is good. Okay, so why is this the parent function? Let's just look at a couple examples. F of 0 will certainly just be 0. F of 0.5, when I round 0.5 down, it stays 0. If I round 0.9 down, right here's my x value of 0.9, it's 0. But once I get to 1, 1 is 1, so it jumps up. Same thing, we continue that. 1.2 would be 1. 1.9 would still round down to 1, but once I get to 2, it actually equals 2. Okay, so you want to memorize this parent function of our greatest integer. Start at our origin, 1 unit wide, and jumps up by 1. So let's look at one of these together with transformations. So here's my greatest integer function. What are my transformations? We have a vertical stretch of 2, and -3 on the inside means to move to the right 3. So I'm going to take that parent function, which usually starts at the origin, but I'm going to move it to the right 3. So instead of starting at the origin, I'm moving over 1, 2, 3 units. Now I'm not changing anything horizontally, so each step will be 1 unit wide. And I'm not moving up or down. There's no vertical shift, but there is a vertical stretch. So instead of now jumping up 1 unit, like in my parent function, I'm going to jump up 2 units. So now I jumped up 2 units, but I'm still 1 unit wide. Again, jump up 2 units, but still 1 unit wide. Or from where I started at 3, 0, I could go down 2 units. And there, that would continue on as many steps as you want, but that would be the graph for this greatest integer function that's moved to the right 3 and stretched 2. Let's do a test point, okay? So if I did a test point, let's say, let's plug in, let's plug in 4.5. If I plug in, so x is 4.5. If I plug 4.5 into this equation, it's saying subtract 3, that would give me 1.5, and find the greatest integer of 1.5. That would round down to 1, so I would get 2 times 1, which is 2. So let's see, when x is 4.5, here's 4.5, and I plotted at 2. Bingo, there it is. Okay, so you can always do a test point to see if it's correct. You try graphing this next one. Think about the transformations and then use those transformations with the parent graph above. Okay, now what we want to do is we want to write a piecewise function. So I'm just going to highlight so we can clearly see what the function is. I think there's supposed to be an arrow there. And we have what looks like the following. I'm going to put an arrow there. I can't tell if there was one, but I'm going to put an arrow there. So in terms of your notes, feel free to put arrows where I put them. Okay, so when I'm writing a piecewise function here, we can see that there are 2 pieces. So we're going to have f of x, and we're going to need to come up with 2 equations. So that's the first thing we want to do is figure out what the equations are. So this first one on the left is a horizontal line. Remember, horizontal lines are always in the form of x equals some constant. Sorry, excuse me about that. Are always in the form of y equals some constant. So let's look at this. What is my y that's being constant? And if we look at that y value, it's 2. So f of x, y equals 2 for this piece. We'll figure out the restrictions afterwards. Now, the second piece is also a line. So that's going to be in the form of y equals mx plus b, right? A diagonal line will be in the form of y equals mx plus b. So we need to figure out what is this guy's slope and what is its y-intercept. Well, we can see the y-intercept is at -4. Now, what is the slope? We can count from one point to the next sort of good point. So at -4, the next one I see crosses at 1, 0. So I went, 1, 0. So I went up 1, 2, 3, 4 and over 1, which means my slope is also 4. Okay, so this equation is y equals, or f of x equals, 4x minus 4. So here are my 2 pieces. Now we need to put in the restrictions. So our function equals 2 forever? No, only for these pieces towards the left, which are when those x values are less than, if we look at this x value, it's -2. So it equals 2 when x is less than -2. And notice it was an open circle. Now our second diagonal with a 4x minus 4, when do we plot those? Well, the furthest to the left that goes is -2, and then it goes on forever. So this is when x is greater than or equal to -2. And there's my equation. Okay? So then we have a few practice problems. I want you to practice graphing this piecewise function. Notice there are 3 pieces. The good news is all 3 are linear. So you should have 3 portions of lines. The second example is a greatest integer function. Remember using that parent graph and then use your transformations. Stretch of 3 and left 2. Our third one is a step function. So make sure that you have 4 different horizontal steps. And the last one is another piecewise function. Why don't I do that one quickly with you? So for this one, we have a line of x minus 4. So I'm going to graph this one in blue. So x minus 4 would mean to start at negative 4 and have a slope of 1. So I would continue graphing that. And so forth. However, remember, it's saying just graph that for all values less than or equal to 3. So here is the 3. I'm going to make it bigger. So I want to erase anything of x values greater than 3, which means at x is 4, x is 5, x is 6, I need to get rid of. So I'm going to get rid of those and then make the connection of my arrows for the ones that I actually want. So there's the blue piece. Now let's graph the second piece, which I'll use orange for. This piece is saying f of x, or y, equals negative 1 for x values greater than 3. Well, look at this. What's happening here is I would start here and I would stay at negative 1 for all values greater than 3. So I'm just going to plot towards the right. What happened with this graph is they actually did connect. This would actually end up being a continuous function because we did have some overlap. Okay, and for number 5, I'll do one of these examples with you and you can do the other one. So for number 5, why don't I do B and you do A? So for B, we have 2 pieces. So I'm going to have 2 pieces of my function. The first is a parabola. So remember, our parabola's parent function is x squared. But what's happening? What's happening to this parabola? It is going to move up 1, we can see. Is it moving to the right at all? Nope, we're still here on our y-axis. How about the stretch? Normally, I should go up 1 over 1, and that is what is happening. So all we're doing is going up 1. There's no reflection, no horizontal shift, and no stretch. So that means that function will be x squared plus 1. Now, when am I x squared plus 1? Does this parabola go forever? No, what's happening here is that it's a parabola for all the values to the left of 2. So what we want to have here is we have this open circle at 2, and then we're going on all the values less than 2, 1, 0, negative 1 are plotted. So that would mean the domain restriction would be for all values x is less than 2. Our second piece is a line, right? So that line we want as mx plus b. Well, let's see. Can we figure out the slope? What's happening here? Down 1 over 1, down 1 over 1. So my slope is negative 1. How about the b value? Well, the b value is not plotted, but I could continue this graph and check it out. We know the slope is 1. So if I was at 2, negative 1. So I was at 2, I'd go up 1 to the left 1. And then I would do the same thing, up 1 to the left 1, which means if I connected that line, my y-intercept will be at 3. So what does that mean? That means, I'll erase this now. That means that my equation for this one would be negative x plus 3. And those are for all values that are greater than or equal to 2. Okay, you fill in the rest of the notes and we will check all your work tomorrow.